So now that we've looked at how these midpoint and trapezoid rules actually work, the important question that we now want to ask is, will these approximations be able to improve? Will they get better? And very clearly you might be able to see that, well, it's pretty reasonable at least to guess that as we were to increase the number of rectangles or the number of trapezoids that we use, that our approximation should improve because the amount of error that we're going to have on each little one is going to continue to shrink down. But another good question to ask would be the following. If I'm trying to approximate areas under very difficult curves, then is there a certain value of n, a certain number of rectangles or number of trapezoids that we could guarantee ahead of time would make an approximation that only has a difference, an error, in relation to the actual area of a fixed amount? Now, to answer that question, we're going to take a look at the following. I'll start by saying that if we trust our calculator, which is a big thing to trust. I mean, it's kind of weird, right? Have you ever thought about how strange your calculator is? Someone just hands you this random electronic box and you type things in and it tells you answers? How do you know that what the calculator does is actually correct? Maybe it's been programmed wrong. How do you really know? But if we trust our calculator, we could type in an integral of e to the negative x squared from -1 to 1. That's what we've been approximating in the last couple of examples. And we could see it, the calculator approximates this as about 1.494. Well, we can compare this answer to the answers that we have from our previous two examples. So I'll start by comparing this to the midpoint rule. What I'm going to be interested in doing is trying to calculate how far off our midpoint approximation was from what the calculator is telling me is a rough approximation of the actual area. So you might recall that in the midpoint rule, we got 1.558 as our rough approximation, and we could see how far away that is from the actual answer by doing a subtraction. Now, this subtraction here, if I was to go ahead and type it in, I think results in a value of 0.064. So this right here is an amount of error. It's how far away we were from the right answer. Now let's go ahead and compare that to what actually happens when we look at the trapezoid rule. So when we dealt with the trapezoids, we got an approximation of 1.368. I'm still going to subtract off the 1.494 because that still tells me kind of the gap between them. But since I don't really care if that gap's negative or positive, I'm going to absolute value. So in fact, I could do that actually up here with the midpoints as well. If I absolute value that, it's essentially saying I want the gap between the numbers, but I don't care if it's an overshoot or an undershoot. I don't care if I under approximated or over approximated. I just want to know how far off we are. Well, in this case, I'll end up with a value of 0.126. And again, this is a value of the error in our approximation. So in this case, when n was 2, when n equals 2, it appears that the midpoint rule gave a better approximation. Now, that doesn't necessarily tell me that the midpoint rule is always going to produce a better approximation. Maybe as I change n, or as I change the function that I'm working with, the trapezoid rule might all of a sudden become more valuable. In fact, our question here again really isn't even which of these techniques did a better job, but more importantly, the question again up here. Is there a certain value of n that can guarantee my approximation is within an error, a specific error of, say, number e, from the actual area? The strange part of what we've shown down here is that we were relying on this calculator value. But what if we didn't know what that calculator value was? What if in place of that number we just had a question mark? What if we didn't know the answer? Could we still predict how much error was in our approximation. Could we say, I know that when I use two rectangles or two trapezoids, my error is going to be roughly this much, even if I don't have the actual area? Well, to help with that, it's actually very surprising that we have this theorem. Now, we're not going to be able to go ahead and prove this theorem in the notes here, but we can take a look at what it says and what it's really good for. Let's see what we got here. Suppose, it says at the onset, that f double prime of x, absolute valued, is less than or equal to k for all x in a to b. Okay, let's just ignore that statement for the moment, and let's keep reading, because this is kind of strange. We'll see here that if ET and EM are the errors in the trapezoid and the midpoint rules, okay, so like these are going to be our red values, ET and EM. They're like these numbers. Notice that means that this top number up here would have been considered EM, and that bottom number down there would have been considered ET. But if those are the errors in those different rule approximations, take a look at what we're saying here. This says if I absolute value that error, right, so that it kind of like what we've done here. If I absolute value it, so I don't care if it's negative or positive, I want just a positive result at the end, then that amount of error is less than or equal to whatever number this thing produces. Similarly, the error for the midpoint rule is less than or equal to whatever number this produces. And while these formulas can look a bit scary, let's just read them through to see how they work. Notice here, b and a are just the interval on which I'm integrating, right? Like I often integrate from a to b, so I should know those immediately at the start of a problem. N is always just the number of rectangles or trapezoids that I'm going to use, and so I'll have that at the beginning of the problem. The only thing that's kind of strange is this value of k that occurs in here. And what we'll see here is that k is a specially selected y-coordinate. It's a y-coordinate so that when I take f double prime of x and I absolute value it, I can select k to be a y value that's greater than or equal to this. We'll see how this works in just a moment. Let's take a look here really quickly at example number 3 to see how we can use this theorem. So I'm going to start here. Suppose we want to approximate, again, the area under this curve with the midpoint rule and n being a 5. Can I automatically, without doing any of the actual midpoint rule rectangle constructions, can I give an upper bound? That is, can I give a cap? Can I give this right-hand side, well, not that right-hand side, but this right-hand side up here, an upper bound, a cap on the error that I might receive when I do this approximation? That is, without building the rectangles, without finding the approximation, can I figure out how bad the approximation might be? How far off of the right answer might it hit? Well, if I see here, from up above, there are just a couple values that I need to determine, and I can fill in this right-hand side. So I'll say here, we see that A is equal to, well, let's see, that's -1. B, that's +1. We're already told n, that's 5. Notice those values come immediately. But k, k we're going to have to think about. Remember what the theorem up above said is that I need to go take a look at the second derivative of my function, absolute value it, and then find a y value that's bigger. So for the moment, I'm just going to put a question mark here. I'll start by saying that f of x is e to the -x squared. And I would have to go ahead and start to calculate down to its second derivative if I want to try to find k. So its first derivative isn't too bad. Notice that for the first derivative, I would say the derivative of e to some stuff is always just e to some stuff, and then chain rule, take the derivative of the stuff, which up there would be -2x. Now, to take the derivative again would be a bit more complicated because it would require that I use a product rule. I'm going to save on some time here and just quickly go ahead and tell you what that formula is going to look like. But if you simplified it down as much as possible, you would get e to the -x squared, and you'd have a 4x squared minus a 2. Okay, so this is my second derivative. Well, now let's go ahead and switch over to a calculator to see what this function would look like, and then how I can use absolute value bars to see what it looks like on my given interval. Okay, so if I have my calculator up here, I'm going to go ahead and go right to my y equals to get ready to graph a function. Now, since I have to include the absolute value of my second derivative, I'm going to start here by clicking the Math button. And if I go over to this number category, you can see that I have an option for an absolute value. If you have a fancy calculator like mine, it'll put in absolute value bars and allow you to fill in the middle. If not, you'll just see that ABS written down, and you just type your function in afterwards. We know that our function was e to the power of a negative x squared, and then we had a quantity, and in that quantity was 4x squared minus 2. So I'm going to go ahead and I'm going to put all of this here in the picture. But remember that the theorem said that I only need to look at this function on the range from a to b. Remember that our range from a to b was -1 to 1. So really quickly, I'm going to go to my window, which might have all sorts of jacked up values in it. And to reset a window quickly, you can always hit zoom and then the number 6. Now again, this is going to reset to the standard 10 by 10 window. And while I can see that I have my function kind of graphed out here, I'm really only interested in it on the interval from -1 to 1. So I'm going to modify my picture one more time to just have this go from -1 to 1 and hit the graph button again. And what I'm looking for on here is something that could serve as a value of k. K again has to be a y value that is greater than or equal to every single y value in this picture. Can you find a y value that is bigger or equal to every y value within the picture? Well, actually, yeah, there's tons of them. Like, look up here, right? Like 10 right at the top. Isn't that bigger? Of course. So that's a possible value for k. But then again, so is 9, and so is 8, or 7, or 6, or 5, or 4, or 3. All those are values. You could choose decimal values in between. You could do 2.5. In fact, it usually becomes advantageous to choose the smallest value possible. And in this case, that looks like the value of 2. So I'm going to go ahead here, and switching back to my notes, I'll be able to see that it seems like we see that the absolute value of f double prime of x is always going to be less than or equal to 2, and that means that I have found a possible value of k. Now with all of these values found, I can easily go ahead and state that the error that's going to happen with my midpoint rule, when absolute valued, is automatically going to be the same size as or smaller than the following. Remember how that formula was set up? It was k times the quantity b minus a to the third over 24n, that should say n squared. 24n squared. So I can fill in all my pieces now. I have 2 for k, 1 minus -1 cubed, all over 24, and I have a 5 squared. Let's see, so this distance here is 2. I have 2 to the third times another 2, so this is 2 to the fourth over, what is that, 25 times 24 in the denominator. So I think this is going to be 16 over 600. Or if you reduce that, that's 2 over 75, or 0.02, and then a bunch of 6's repeating. You could double check my numbers on that. But notice that what we've been able to say is that if I was to approximate the area under this curve with 5 midpoint rectangles, I know that I'm probably not going to hit the perfect right answer. So how far off is my answer going to be? My error in my approximation is either going to be equal to this value over here, or it will be smaller. So I'll say thus, the error in this approximation, error in this approximation will be 2 over 75 or less, right? It's equal to or it's less than that amount. That's pretty awesome. We can do this, and notice we can do this without ever actually having the actual area. Now, part of the additional advantage of this is if I take a look down here at question B, I can see that I can kind of reverse the type of question that we answered up in part A. The question here is, how large should we take n if I want to use the midpoint rule and get an approximation that is only this far away from the right answer, right? I want this or less. Well, the question here then is, how many rectangles do I need to use? Should I use 10 rectangles or 50 or a million? Like, I don't want to start guessing and doing all the rectangle construction, but I can see really quickly how to actually work with this. Take a look. I can say that we know that the error in the midpoint approximation is automatically going to be less than, and I can start to set up what we saw up above. It's going to be less than k times b minus a cubed over 24 times n squared. Well, if I fill in the values that I still know from up above, notice now n is the only value that I don't know. I can still see I'm going to get 16 over 24 times my n squared. Right? Remember, 2 went in place of k, and the distance of the interval was 2. Well, what I really want then is, if I know the error has to be smaller than or equal to this, if I can pick an n that can make this smaller than 1/1000th, then I can guarantee that my error is smaller than 1/1000th. So I'll state down here, we want this error, which we know is less than or equal to this amount. If we could make this less than 1/1000, we would be good to go. Because if this is true, and notice I'm going to mark this with a question mark because I don't know if that's always true. But if that part's true, then certainly this will be smaller than 1/1000th. Well, to figure out if that's actually the case, let's go ahead and solve this inequality. So I'll say we need to solve here this little inequality. Now, fortunately, everything on both sides is positive, so when I start multiplying things around, I don't have to worry about changing the order of that inequality sign. So let's see here. If I multiply over this 1,000 and my 24n squared, I'm going to get 16,000 should be less than 24n squared. Of course, that should take me to, if I divide both sides by 24, you can double check me, but I think I get a fraction that can be written as 2,000 over 3. That should be less than n squared. Of course, if I square root both sides, I end up with the square root of 2,000 over 3 should be less than n. And now I can start to search for n values that are roughly going to be or that are going to be greater than this square root value. Well, if I switch back to my calculator here really quickly, I can see that if I was to do something like the square root of 2,000 divided by 3, that's a value that's roughly 25.8. So what values of n, what number of rectangles would be greater than 25.8? Well, again, if I switch back here, this seems to then imply that n would need to be bigger than 26, since again, what we have here is this value being about 25.8. Here, though, I don't just have to say bigger, I could say bigger than or equal to. As long as n was 26 or more, I would be good. As a conclusion, then, I can really state over here, so if n is equal to or bigger than 26, then our error will be less than 1/1000th. If you think about this, this is actually really, really powerful because this allows us to take, again, extremely difficult integrals and that we can actually begin to approximate them, but more specifically, I can predict ahead of time how much work will be required to get the level of accuracy that I want. And in a lot of applied fields, I don't actually need an exact, precise answer. Maybe I just need an answer that's accurate to, 50 decimal places or something. Right? Well, I can actually predict ahead of time how much work I will have to do in approximating to get that level of accuracy. That's a really, really powerful idea.